All right, hello everyone. Welcome to this IEEE Communication Society event. The title of this event is Scaling Enterprise Internet of Things. And our speaker today is Abhishek Bhattacharyya. He's a senior technical leader at Cisco, where he plays a pivotal role in advancing indoor Internet of Things solutions through Cisco Spaces. His work focuses on architecting and scaling management systems that enhance the automation, security, and resilience of enterprise IoT deployments. He has several publications in international journals and conferences, and he holds multiple US and international patents. He's part of several standardization initiatives as well. Abhishek holds a Master of Science degree in electrical engineering from Stanford University. Thank you, Abhishek. Thank you.
Thank you, everyone. Let's get started. So, we are going to mostly talk about enterprise IoT and the scales of how to scale enterprise IoT beyond, small deployments, which is generally, the POC kind of deployments which you generally see in most laboratories, right? So the agenda is we'll first go through introduction of enterprise IoT. I mostly focus on commercial enterprise IoT, and there are other teams in Cisco which focus on industrial enterprise of IoT. So I'll mostly focus on the commercial use case here. And then we'll discuss some of the use cases for enterprise IoT. Then we'll discuss some of the common architectures which we see in the field. Then we'll go into the crux of the talk, which is the scalability part. What are the metrics, what are the targets for scales which we are seeing currently? And then finally, we'll go into the details of how we are enabling scale, some of the innovations we have done, some of the challenges and problems which we see. So enterprise IoT is basically, you can classify it broadly into commercial and industrial. Commercial is offices, hospitals, malls. These are buildings mostly. Some people call it building IoT as well. While industrial IoT is mostly factories, power plants, logistics hubs. The technologies which you use in commercial and industrial IoT are different, and also typically the way you scale commercial and industrial IoT are different. In industrial IoT, you have lots of 5G connectivity. In commercial IoT, you basically generally have gateways which are deployed inside the buildings, which are basically scanning for IoT devices. So if you look at commercial IoT, the growth is about 10% year-over-year growth. Similarly for industrial IoT, that is also the case. Other important thing about commercial IoT is that there is a significant difference between commercial IoT deployed by companies which also manufacture gateways. So typically what will happen is that most buildings will have a Wi-Fi infrastructure, so access points which can act as gateways. So if you have access points already deployed, the growth is somewhere around 20% year-over-year because you don't have the additional burden of deploying gateways as well. But if you do not have, then you have to deploy additional gateways, which is another cost which stacks up. So what is the aim of commercial IoT? The aim of commercial IoT is to convert buildings into smart spaces. So typically with your Wi-Fi access point infrastructure, you'll generally have connectivity, but the same infrastructure you can leverage to deploy additional use cases, for example, space utilization, environmental monitoring, patient experiences in hospitals, and so on. So the main idea behind commercial IoT is that your entire network basically behaves like a sensor. So you can have your access points which are scanning for different kinds of signals. And then using those signals, you can use different algorithms to do indoor positioning of devices. And once you have the indoor position of different IoT devices which are transmitting wirelessly, and you can use your network, then you can basically enable different use cases on top of those. So if you look at mostly the devices which will be used in our sensors, tags, and beacons. And in commercial IoT, you basically see both consumer and industrial grade devices, which is very different from industrial IoT. Industrial devices are much more hardened. Commercial devices are prone to failure. And even in different cases, we see there are lots of connectivity and reliability issues. Connectivity is mostly through Wi-Fi, Internet, Ethernet, Bluetooth, Zigbee, Thread Matter, which is coming up. And then Localization technologies are usually through Wi-Fi, BLE, UWB. These are different radios which are already there in the access points. Latency requirements, I'll come to this later on. There can be critical and non-critical use cases. Data rate, again, depending on the use case, in some cases there can be significant data rate, like I'll come to the data rate later on. In terms of protocols, most of the commercial IoT devices will either transmit data through wireless mediums, or if they have a direct connectivity, they'll use MQTT, a CoAP, some kind of a protocol to basically compress and send the data. Lifespan is a big issue in IoT. Most of these devices are battery powered, usually last 2 to 5 years. Sometimes the devices have to be replaced often, depending on the use case. And firmware upgrade, virtually nobody does. So basically you buy a device, you deploy it, and you forget about it. So I'll briefly talk about how most of these commercial IoT systems are set up. So on the left-hand side, you will see there are different data sources, and these data sources can be from different sensors, switches, access points. All these data are basically scanning your physical space and being ingested by some gateway. And in this case, the gateway might be an access point or some other specialized gateway devices which you have deployed. Once that is deployed, you basically add context to the signal. So you basically figure out, where is the signal originating from, right? What is the area of the building? What is the asset? Where is the signal actually coming from? Then you basically make sense of the data. So you have positioning systems which trilaterate the signals and basically give you an interlocation. You also have some way in which you can parse the telemetry which is being broadcasted by these devices. And then finally, you standardize and send this data out to different applications who will consume this data and basically enable different use cases. And the use cases can be, smart workspaces, operations, and venues, and so on. So I'll come to the use cases now. Some of the most common use cases you will see in IT is, one of them is auto-locating access points in a building. So typically it's a very problematic situation, because if once a building has been laid out and an access point has to be moved from one location to another, you have to update maps and so on, which is extremely hard to do. So what we do is, in our access points, we have a GNSS module. So some of those GNSS modules, if it is very close to the edge of the building, it will basically get a latitude, longitude, or some kind of a position. Then once you have that position, you can use that as an anchor, and then use fine-tuning measurement, FTM, to basically relatively position the other access points relative to this access point. And thereby you can create a graph and basically figure out where are all the access points located in this building. And we do it more or less within, very less than a meter accuracy. Most of the access points are located. The other thing is secure Wi-Fi onboarding. So whenever you go to yes.
So the basic idea is to use GPS to establish a map so that you can relocate your stuff when moving to a new place.
No, the idea is that we have access points in the buildings, right? So when you say move an access point from one place to another, so everything is located relative to the access point, okay? All sensors are located relative to the access point. So if the access point position itself is wrong, whatever sensors you locate in the building will be wrong. So what you do is you basically fix one access point. Essentially, you need to get a set of access points location through the GNSS module. The GPS module does not work inside the buildings, right? So mostly if you are close to the window, the GPS module will basically give you some location. And then you basically use FTM. There are different technologies. We use FTM, but basically you use that to locate relative to this access point where all other access points are located. The other one is secure Wi-Fi onboarding. So for example, let's say you go to a hotel, you get a splash page whenever you connect to the Wi-Fi, right? So now we can detect where your phone is. So if you are, say, in the lobby area, you'll get a different splash page. You go to some other area, you'll basically get a completely different splash page. The third one is the biggest use case. I would say about 80% of the use cases in commercial IoT is asset tracking. And there are different technologies for asset tracking depending on different requirements. So some technologies, for example, will be, I want to track assets within 5 meters, some will be within 1 meter. So it depends on different use cases. And the last one is basically identifying rogue devices, which there is a requirement more or less which the government has to essentially figure out if this asset belongs to actually you or not. And so there are lots of companies who basically have wireless intrusion prevention solutions. So there are different ways to package this, but the basic idea is, does this device belong to you or not? The next one is smart workspaces. So digital signage, we'll see a demo of this. What happens here is that you have a screen in front of you where you can basically go interactive with it, and it will tell you what is the air quality inside the building, what is the, what is going on, in terms of the which rooms are available for, booking, how many people are inside the rooms, and so on. Then we have indoor wayfinding, which is like Google Maps but for indoors. So you can basically just scan something and start wayfinding. Then you have space utilization analytics. For example, is this room occupied? How long has it been occupied for? What is the number of people who generally use the room? Then you have smart rooms. We'll again have a demo for the smart rooms where you'll be able to see, how we can control for example, the air quality inside the building depending on how many people are there in the building. And this is smart venues where you basically have contextual engagements. For example, you sometimes visit a store and you get a notification in some area of the store. So there are IoT devices which can detect your presence and basically push a notification to your phone if you already have an app for the store. Behavior analytics is things like how many people are actually, let's say you're shopping and there is some areas in the store where there are a lot of people, there are some areas where there are not a lot of people. So we basically figure out dwell times of areas inside the building, inside the store, in different areas of the building. And the last one, and this is where the latency critical use cases are. One example is infant protection. So if you in hospital when a baby is born, you will see that they put a tag on the baby's feet so nobody can run away with the baby. So effectively, what we have to do is there is a requirement for a sub-second.
You might be services as
Sure.
the microphone. We have handheld microphones in the back for Q&A.
Yeah, I'll just continue. So for infant protection, for example, you have to detect within a second whether this baby has left the building or not. So that's very critical. Asset tracking, I already said. Temperature and condition monitoring is essentially you want to monitor the temperature inside a fridge which is storing blood, right? So it's very critical in those cases. Staff duress, for example, somebody presses a button and you have to do an emergency response. We have schools where you have emergency buttons, you have hospitals with emergency buttons. So all this has to happen within a second, so effectively. So I'll go through some of the demos. Let me see if I can play this.
Hi, I'm Simon. I'm joining you all from the Cisco office at Bedfont Lakes. This is a Cisco Smart Space. Yes, exactly. So this is where we have our smart workspaces experience. This is where our end users can come in and find free meeting spaces and desk spaces. We can see here that Darwin is a meeting room that's currently available for us. It doesn't have anything in the calendar for today. We can understand things like the occupancy, the air quality, the temperature, the average humidity of that space. And we can actually jump in and get directions to that environment. This is going to allow us to navigate to that space in the quickest available route. We can take this over to a phone experience as well by scanning the QR code down in the bottom left. As we scan that QR code, we can launch an app clip experience. This is where we're allowing users to stream an app to the phone, so nothing actually needs to be downloaded. As we open that app clip, we have the ability to navigate to Darwin, that meeting room that we've just found. And we're going to get turn-by-turn navigation about how to get to that space. As we start moving, Our position will be updated and we just have to follow this blue line. It's going to show us right to the door. Great, so now we've arrived at our meeting space. We can see the room's still free and we can head in. So welcome to our Workplace Operations Center. This is where our facilities managers can get an understanding of what live occupancy looks like from across their environment, understand things like air quality and CO2 levels, and get a deeper dive understanding and start to understand alerting on temperature and humidity and ambient noise from across their space. We then move over and look at things like space utilization. What does the average meeting look like? Are users booking rooms? Are there ghosted meeting rooms? How does the space utilization actually fare? Do we have users using 10 people meeting rooms as a single person office? How's the utilization of that space? And it allows our facilities managers to understand if they were to respec their environments, what would their perfect space look like?
So this was the digital signage and wayfinding and space occupancy demo. We'll just do a quick demo of the smart rooms.
Let's see what it is. Here inside is a room that is measuring the occupancy, the air quality, CO2 levels, and controlling the airflow within it. Right here is a portable VAV which connects with your building systems and is in real time adjusting the air quality and airflow in the room. It's counting the number of people, including my buddy Julian, who's doing the camera. There's 2 of us in the room. It's counted the number of people. It's moving in from a sustainable mode to a well-being mode where the air quality of this room is being adjusted. Proceed.
Okay. Now I'll transition into the architecture part. So these are more or less the use cases which we're enabling. Now I'll go into the architecture part and then I'll come back to some of the innovations which we have done to scale it to that extent. So typically for the architecture, what you'll see is, hello. Yeah, so what you'll see is at the bottom there, you have a lot of sensors, and all this sensor data basically gets collected by gateways, which can be, access points, switches, even, collaboration devices like your WebEx devices and so on. Then all this data is aggregated and basically passed on to an edge. In some cases, these gateways are directly connected to either a internet or some other system, right? Now this edge basically is very important because, as I'll say, that there is a lot of data coming in, and if all the data goes to the cloud, it's basically overwhelms the cloud. So this edge processor is where you basically run different kinds of algorithms, where you basically learn machine learning algorithms and all this as much as you can. You try to compress the data, reduce the data, and then basically forward the data to the cloud. Some of those algorithms you can also run on the gateway if you have enough power on the gateway, if you have enough CPU processing power on the gateway. But most of the times you will basically run it on the edge. And then in the cloud, you definitely have different maps. I'll talk about the maps, location service, management service, and then APIs, right? The APIs will be consumed by third party to basically, to consume the data and enable their use case. And there is also a way to consume data from these low latency APIs. So this will be use case for critical use cases like infant tracking, right? You do not want the data to go to the cloud. You want the data to go to the monitoring or alerting system as close to the sensor as possible, right? So the sensor will broadcast, it will go to some access point, and from the access point to some APIs, you'll be able to basically transmit the data to some other party who will be able to produce an alert. So this is sort of the data flow. And then I'll describe a very painful process currently to show the control path, how you control these IoT devices. And you'll see that why it is so broken and why scaling is so difficult as I go through the process. So typically what happens is that suppose some vendor wants to manufacture a device, right? They'll work with a device manufacturer that I'll place an order of 5,000 devices, and they'll be shipped and held at the distributor, which will be, essentially, some company holding just the devices and waiting for orders, customer orders to come in. And this is where the entire complexity comes. So in consumer IoT, when you order a device, you basically can scan a single device at a time, right? And basically add it to your system. You have a Nest thermostat. You basically add Nest thermostat to your Google account, right? But in enterprise, when you have 10,000 devices, you cannot do it one by one, right? So effectively, what you really need to do is to get some kind of an ID through which you can bulk onboard these devices, bulk provision these devices, and that's why there is a lot of complexity which comes in. So the typical flow is the customer, that's number one, will order to some order management system, right? Some website where I want 500 devices, right? And that goes to the distributor who is holding these devices. Distributor will ship these devices. That's essentially number two here. Distributor will ship these devices and let the order management system know that I have shipped these devices. And this order management system will now let this cloud management service, in case of Cisco or other IoT service providers, that I have shipped these devices and these are the MAC addresses or some identifier of this 1,000 devices, 500 devices which I have shipped. Now the consumer also gets an email, and the consumer will go here and tell, I want to claim these 500 devices in my account. So they'll enter some order ID through which these all 500 devices have entered into the system. But now this cloud management system has no idea what these 500 devices are, because the manufacturer has no idea about it. Because the distributor has no idea about it. The distributor basically has a list of devices it has shipped. Now this cloud management service has to go out to some kind of a vendor, the device vendor, and tell, I have this list of 500 MAC addresses, tell me what are these devices. And this device vendor has to tell the cloud management service that, okay, this is an air quality monitor. This is some different kind of sensor, right? So there has to be a discovery of a device in order for the device to be provisioned. Once the device discovery has happened, now the cloud management service will basically push that data to the edge. The edge basically goes to the gateway, which are the access point, and the access point basically provisions these devices with all different kinds of keys and stuff like that, right? That's the typical flow. There are some variations on this flow, but that is more or less, how it is commonly done in the industry. Now I'll come to the scale metrics. So in terms of Cisco Spaces today, we have 300,000 buildings which are live with Cisco Spaces. It's almost 10 billion square feet. So I've just given a reference. New York is around 13 billion square feet. So around 80% of New York. And then we have 4 million access points, which are basically scanning constantly the environments. We have 20 trillion location updates coming in on almost a daily basis. We have 2 million tags which are constantly monitoring. There are about 750,000 devices we are managing, hundreds of device types. And then we have around 25 apps which I've built. It's like the App Store model, Apple App Store. So Apple provides some native apps. So Cisco Spaces also provides some native apps. And then there are hundreds of partner apps which we have built, which are like developers who are working with us to basically build apps. So coming to location accuracy, again, depends on the technology. So we have both Wi-Fi, BLA, UWB location accuracy. So for Wi-Fi, you typically will get somewhere around 5 to 7 meters. Depending on the environment, in some cases, if the APs are dense, then it will be much better. With case of BLA, you will get somewhere around 3 to 5 meters. With UWB, you'll get somewhere around 1 meter accuracy. So if you want room level accuracy, you generally go with BLA or UWB. If you want, some area level accuracy, you go with Wi-Fi. So it depends on your use case, how do you want to track. Latency, we basically say, 95% of the packets will deliver at less than 5 seconds. Priority packets are treated differently. These are like, some staff duress button presses and so on. Availability is there. Now coming to the volume of the messages which you process, you will see somewhere here, the gateways will generally process somewhere around 300 messages per second. The edge processor will somewhere process around 200K messages per second. At the cloud, we are dealing with somewhere around 3 million messages per second. For reference, Google processes, Google search is around 200K per second, 200K searches per second. And WhatsApp is around 1.5 billion messages per second. So it's more or less, currently it's around, 2 times the scale of, WhatsApp, or, almost 10 times the scale of Google search. And each of these messages we not only process, we decode the telemetry. So basically there is decoding involved, and also we use it to do localization. So we basically use it to locate the devices. So there is a lot of computational complexity which goes in for every one of these messages. So now I'll come to the scaling part. So I've divided into different parts, including the partner ecosystem. So I'll go through all of the parts one by one. For scaling the partner ecosystem, one of the biggest problems is software rollouts. Okay, so this seems very trivial at the beginning, but so we have been in existence for about 8 years. For the first 4 years, we had very limited adoption because we tied our gateways, which is access points, to the devices, and this is very common. So if you have a device and a gateway, and every time you have to update the device, you have to change the gateway, it becomes a very problematic scenario because this is very low-level code. So what we do is that, so customers are just unwilling to upgrade these gateways or access points just because you have to just because you're rolling out some IoT solution, right? So what we do is that we make sure that the gateways which we run on the access points are containerized, right? So we are able to deploy it directly from the cloud. So there is no need to basically change an access point image in order to deploy a geteway. You can just run it from there. Also, what we found out is that most of the IoT vendors are basically small companies, and the developers are very limited in those companies. They're mostly familiar with RESTful interfaces, not with low-level firmware embedded code. So what we realize is that it's much better to integrate with these companies at a higher layer than at a lower layer. So there is an IETF standardization initiative going on where we have, for non-IP devices, how can you control those devices over a RESTful interface rather than at a lower layer. So the other major issue is interoperability, right? One vendor's device, and this is there is a vendor lock-in in most IoT systems. One vendor's device you cannot use with another vendor's server, right? So what we have to do here is to decouple the device with the application. And there are two different ways in which we do this. One is we auto-decode incoming telemetry messages. Means if a device is broadcasting a message, we do not know how the telemetry inside it is structured. But we use different machine learning models to identify that what is a possible structure for this message. The way we do it is our access points basically have sensors in them. So an example would be, let's say this access point is giving a temperature of 65. And we know that there is a sensor somewhere in the vicinity which has a temperature sensor, right? So I know that somewhere around 65, the value of 65 will be somewhere there in the byte stream of this device. When we basically search for this 65 in this byte stream, we figure out that there is a 65 here. Then we see how this changes as the access point's temperature reading change in the future, and whether it correlates with the reading. And that's how we figure out that this byte is most likely a temperature byte. Similarly, for those other sensors, so we basically use known decoding techniques to basically identify other devices which can be, which we know about, which you don't know about. The other part is we standardize outgoing messages, and this is very important because different devices will broadcast messages in different formats. And the applications which will consume these devices, they have to work with the device vendor. So what we do is we standardize the format so that anybody who builds applications on top of our format can independently swap out devices. So you can buy device from vendor A, but application from vendor B, and it will work seamlessly, right? Next part is scaling onboarding, and this is a part which we discussed earlier, is that in order to onboard a device, you need to know what type of device it is. And this, because when you onboard, you just get MAC address, you have to do a device discovery from the vendors. And it's very hard to know that which vendor has manufactured this device, right? So there is a IETF standardization which is going on about, how to represent device models. So there is a standard way. So people who are familiar with, BACnet and other building management protocols, there are ways to represent devices as objects, properties, actions you can take on devices. So that's the same thing which we have here. So these models, the idea is that there will be an online repository of these models, and any vendor can basically go look up these models and figure out what this device is capable of doing. The next part is secure onboarding. This is, I think everybody knows that most IoT devices in the market are insecure, and most are vulnerable to day zero attacks. Like everybody does secure LE, which is vulnerable to day zero attacks. Telemetry broadcasts are heavily unencrypted. Even in hospitals, you can go and scan and see, patients' data going out in the air without any encryption. Firmware is rarely updated. Keys are almost never rotated. So you basically have a device manufactured with a key. The key stays with the device forever. And the main reason is the reward outweighs risk in most cases, because these are very cheap devices, mostly in commercial IoT. So developers don't really have an incentive to put resource towards, managing all the security issues for IoT devices. The problem is there is no standardized solution. And third-party devices I have seen, they have implemented various schemes, including very silly schemes like putting private keys inside devices and so on. So there's a wide plethora of things. We can do regular. So what we have implemented is we basically have regular firmware updates at scale. We can roll out firmware updates across thousands of devices. So every time there is some kind of vulnerability which comes and some vendor basically releases a firmware image, we'll automatically get that image and basically roll it out if you have those devices in your environment. We also have custom schemes for encrypting the telemetry. So effectively what happens is that people don't encrypt telemetry because encrypting is very a costly operation, right? So what we do is we have ways where you can encrypt a part of the telemetry where it might be, where there might be sensitive data, leave the other parts out which are unencrypted. We also do key rotation which are battery dependent. So we reduce the frequency of key rotation as the battery decays. And we also set up multiple key sets at the time of onboarding which can do, so the device there basically says at the time of onboarding, we have say 5 key sets. The device will basically say, I am using key set of index 1 to encrypt the telemetry. And the cloud side knows that I have to use key sets of index 1 to decrypt the telemetry and so on. So we basically just use a single byte to do it. So the next thing is the bulk provisioning of IoT devices. What happens here is, if you have to provision thousands of devices, it's extremely hard. So we never actually provision a device. So the customer basically goes and provisions a location. So you basically say this area or this asset class should have this configuration, right? And as the devices you place in that area or in this asset class, it automatically inherits that configuration. So even if tomorrow you take this, say there is some temperature monitor on a refrigerator, you take it out and place it in another refrigerator, it does not really affect, because it gets auto-provisioned, auto-configured. The mapping solution, so lots of areas do not have maps. People have low quality or partial maps. What we do, we use GANs and CNNs to basically figure out if there is a partial map, how can we complete the map, what is a proper way of, what is the most likely map, and then we also do things like, if you have a CAD file, we can generate rich maps, and then these rich maps are used for navigation, interaction, and so on. So for scaling device management, one of the main things is figuring out what is the closest gateway. So Bluetooth, for example, I have to configure this device, I have to find what is the closest gateway or access point to this device, right? And in order to do that, one of the main problem happens is that Bluetooth has around, say, 90% accuracy, right? 90% connection success rate. So we basically identify gateways which are prone to failures more, right? And we basically deprioritize those gateways and find out other gateways which can handle those. We also do something like virtual max. So if a device is mobile, we can do configuration at the time of mobility that the device all the gateways max at the same to the device. So basically the device does not really understand that whether I'm moving from one gateway to another, and basically maintains a seamless connection, and we exchange the keys between the gateways and so on. Troubleshooting, we have things like active and passive troubleshooting, event tracing, MAC tracing. So we can you can target a single event, and we can basically say for at each level what is this event doing. We enable logs. So the way it works is that we have logs from these different devices which we can take. Then we can group the logs based on different machine learning algorithms into classes, and then we can label the troubleshooting areas for each of the classes of the logs. Again, batteries, we basically are able to predict lifetimes of the batteries depending on different machine learning algorithms. There are simple regression models as well. High value assets, again, this is anomalous behavior, detecting anomalous behavior. We have SVM based models to detect anomalous behavior of devices, what it's supposed to do, and so on. Battery, most devices are battery type powered, like I said, and the more you transmit, devices basically tend to die faster. So what we do is, as soon as a device comes on, we do a auto battery and transmission frequency calibration. We basically figure out this device has to meet these use cases. What is the lowest amount of power which we can do so that all these use cases are met. We use different internal sensors to reduce transmission as much as possible. So virtually, it sleeps for really, really long periods of time. And on an average, what we have seen is that any device which you use in any other, gateway management system, you bring to our system, we can increase lifetime of almost 2 years just by, reducing the frequency of transmissions and, the transmission power and so on. So scaling telemetry. So what I have said is that, one of the main things was the latency sensitive use cases where you basically do not even let the data get to the cloud. You get it as close to the edge as possible. We support priority bits. So essentially, if you have some kind of a priority set in the message, we'll route your message differently, depending on how much priority we assign to it. And the other part is our cloud is distributed. So we do not want the data to go through the public internet system because it's prone to congestion. So what we do is that we route it to the nearest edge and then use our own backbone, which is much faster than the public internet, to basically get it to our processing servers. Again, this is basically just reducing traffic volume so that we can basically get as much into our cloud as possible. The main problem in reducing traffic volume is if you drop too much traffic, your location accuracy goes down. And if you allow too much traffic, then essentially you're processing more and you're basically spending too much resources for that. So somehow we figured out a way in which to optimize this, where the location accuracy is within the range and the data is not too much. We also have different kinds of filtering lists which I've done. We also auto construct forwarding rules. So essentially we figure out what is the behavior of this device, and then we create a forwarding rule for this device automatically. Message rate. So what we do is for message, the key challenge in IoT is that there is a lot of message. It's not really the number of devices. You can have millions of devices which broadcast very rarely. It does not really matter. But if you have one device which is broadcasting 10 or 20 times a second, then you're basically overwhelming the system with millions of these devices, right? So the message rate, what we do is we make sure all the lookups which happen to route this message are order one lookups. So we basically never parse or do anything with this message almost ever until it reaches where it is meant to be parsed, right? So we basically have specific byte streams which are attached to the top of the message, where it's order one lookup on the byte, and then you basically route it to the next hop. And again, we have message-oriented middleware. So these are like distributed queues in the cloud, where you basically there are different hops different servers which can read from different partitions and basically process these messages. That's all I had. Thank you so much. So yeah, please feel free to.
How do you manage traffic? Like if you have a really dense deployment and you have a lot of IoT devices, how do you manage if you have like a lot of broadcast over Bluetooth and Wi-Fi and all of this happening at the same time?
So if I understand correctly, the question is if there is very dense deployment in an area where there is a lot of traffic going on, and then how do we, so the first thing is Bluetooth and Wi-Fi are generally not interfering. We have two different radios, Bluetooth radio, Wi-Fi radio, there are multiple Wi-Fi radios. So essentially the idea is that we can scan the Bluetooth and Wi-Fi separately. So that's the first part. The second part is if there is a lot of data for both, we generally have a way to identify which data might be important, right? So there are two different algorithms which we use. One is based on the power levels. So you can basically set that below this power level, I do not want to get any data, something like that. The other is based on priority bits. So you can say if there is a priority bit set, that gets priority over others. So it depends on the use case. But effectively, if it really overwhelms the radio, then there is no way. Like the radio basically has, like I said, it can mostly do 300 messages per second. If beyond that, you have to figure out some way to prioritize and deprioritize. Yes.
So sorry I came in. There was a slide about the distributors not knowing anything about the devices themselves.
Right. The distributors, yes. I think, yes.
So what is the solution to this?
So there are different ways in which this is being planned to solve. So what happens is that the distributor is just a company which holds these devices, right? They have a storage facility where they are storing boxes of devices, right? Then an order comes in, they will ship a certain number of boxes to a certain address, right? That's all that happens. And what they give is a receipt that I have shipped these devices, right? These boxes, right? Box numbers. Now, what is in that box number is not the job of the distributor. The distributor is holding IoT devices, it's holding bananas. There is no guarantee what it is holding or not holding, right? So effectively, the distributor is shipping these devices. And then what we do is, the solution currently is, the idea is that for every device, we are going to have a model of the device held in some internet repository. There is a IoT standard which is going around, which is called MUD, Manufacturer Usage Description, which is similarly, it's a server, basically a public server with a list of all different device types, right? So now when this device gets shipped and say the distributor tells that I have this MAC address, I've shipped this MAC address. So from the MAC address OUI, you can more or less figure out which company does this device belong to. Now you can go to that manufacturer usage description, identify, that this is the model of this device, basically, and then for this particular company, these are the device types, this is the model of the device, this is how I can interact with this device, these are the messages it responds to. So that's the general, idea behind this, but it's not really popular and it's, just being proposed. There is a review going on. So that is something which, lots of companies are debating how to do it. So it's still an ongoing field. It's not a solved problem.
Just one more.
Sure.
This is about network congestion. So could you tell me how, if somebody had to plan a network with an IoT network with a lot of devices, how do they design their network to avoid different types of congestion between the devices themselves or other devices in the network?
Are you talking about the congestion between two devices, like multiple, it's like a mesh kind of solution, or are you talking about the congestion at the backhaul where you basically get the data and you route it to different?
Actually, the one that you said where they would where the IoT devices are broadcasting
right
messages to each other, and you have multiple ways to ignore some messages or just forward them based on some bits. So, what happens when there are devices from other vendors as well?
Right. So there is always a limit of a system. Okay. So you cannot There are different ways to increase that limit, but there will be some limit you will hit at some point of the time. So currently we do priority based, like I mentioned, we can do a priority bit based forwarding, or we can do things like, there are some cases where we can also deploy gateways or nodes which are completely outside the normal backhaul. So for example, there can be dedicated gateways which are scanning only for certain kinds of devices, if that device is really important, right? For example, you have a heart rate monitor which you really want to prioritize. You can basically tell this gateway, ignore everything else and prioritize only the heart rate monitors, right? So it will basically scan for that. So typically what we see, so there are two different techniques out of this. What we see is that the radios will generally pick up, so you have to remember that when a device broadcasts a data, there are multiple gateways which can hear, right? There are 4 or 5 gateways which can pick up. So each gateway will generally have somewhere around 90 to 95% chance of picking up in a very, very dense environment, okay? Because of the packet rates and so on. So generally a 90 to 95% chance of hearing this device, right? The remaining 5 or 10% is basically, it may not hear. So what we generally do is that if it's a really important broadcast, we tell that device to broadcast multiple times, like it will send a burst of that packet and then again go to another channel and send another burst and so on. So essentially the idea is to increase the odds. That's basically all there is to it. You basically increase the odds as much as possible. And so when this burst happens, we typically can pick up around 99% of the packet. So you're more or less confident you'll, definitely get through. Yes.
You had a slide about interoperability, right?
Right.
You don't tie application to hardware.
Right.
So how do you achieve that? How do you
So the main idea is standardization. You see, all these devices which are here can broadcast data in absolutely different formats, right? And the idea always has been that if you buy a device from me, you have to buy the server from me also, right? And that's where the subscription model has been, that if you have buy a server from me, you basically are tied to my ecosystem. So what we are trying to do, as you get this data coming in, we are trying to standardize what is the output, right? So no matter what device you bring in, the temperature will always be in the temperature field in the output. So if you are writing an application, you can forget about if this customer has bought this device or not, right? What you are thinking is that I have to read the temperature from this temperature field. I do not care what this customer has bought. Tomorrow the customer can buy something else. My application will still function, right? So that's the main idea behind the standardization of the APIs. The problem is the industry is not standardized. There have been lots and lots of, from 1980s onwards, people have tried to standardize these outputs. It has not happened till now. So I do not see, this globally there is a standard which is going to happen.
So the standards are controlled by a bunch of companies.
Yeah, a bunch of companies. For example, we have our own standard which we are basically setting, right? And there are vendor ecosystems who work with us. They will build applications to consume our standard. We are trying to have that standardized through IETF. And there are, different companies which are participating with us. So effectively, that's how the entire ecosystem is evolving. But I would say, there is no standard as such globally that tomorrow if you go to some other